Good morning, everyone. Welcome to the very first EPOS virtual coffee break. My name is Carl Stubbe. I'm a communications specialist for the European Plate Observing System. This is the first of our series of virtual coffee breaks, as I said. And we really hope this will be a place where researchers who have utilized the EPOS platform, who've been supported by EPOS, or whose research is in alignment with EPOS's mission can come together and share the impact of their research because it's something we're very interested in helping diffuse some really interesting solid Earth science research. Just some housekeeping notes. I will be recording the meeting and we'll be reposting it on social media as a in case you missed it sort of thing, because maybe not everyone could make it to this afternoon session. And there will be time for questions after. We can take questions in the chat, or people can utilize their audio at the end of the presentation. And I'm going to give a really brief intro to EPOS, like maybe 1.5 minutes, 2 minutes. And then I'm going to introduce the topic. Then I'll hand it to Frank. Frank will introduce himself very briefly and then hand it back to me and we'll kick off the conversation. So let me just share my screen really quickly. So about EPOS, the European Plate Observing System is a pan-European research infrastructure that integrates data, services, and facilities to study the solid Earth. And we are present in over 26 countries. We have the map here. EPOS connects scientists and national observatories to provide open access to high quality information so we can better understand how our Earth works through the lens of multidisciplinarity. And multidisciplinarity is something which is really important to us, and I'll be mentioning it later in the coffee break. EPOS enables the combined use, and that's key, the combined use of diverse data sets and tools, and supports cutting-edge research and innovation in the areas of solid Earth science. And at the heart of our mission is to make it easier for researchers and decision makers to access reliable data, tools, and services so that these researchers and decision makers can better understand natural hazards, manage resources, and improve safety and sustainability for all of society. And the EPOS research infrastructure brings together the highest quality data and services from the 10 different disciplines. And in EPOS, we call these disciplines thematic core services, or TCSs. And let me quickly introduce you to these 10 different disciplines, and then I'll explain after how we integrate all of their data. So in no particular order, at EPOS, we have volcano observations, tsunami, seismology, satellite data, near-fault observatories, multi-scale laboratories, and our speaker today, Frank, is involved in multi-scale laboratories, GNSS data and products, geological information and modeling, geomagnetic observations, and last but not least, anthropogenic hazards. So how we bring the data and the services of these 10 disciplines together is through the running and the curation of the EPOS platform, which is a totally open access, fair data principles platform. So it does not require a login or you to sign up for anything. You can just go and use the platform. And all of the data from those 10 different disciplines are integrated, interoperable, and it's coming from over 500 plus different providers. And it's gives you some really interesting insights. Like I said, you could layer all of these different disciplines and pick an area on the map and get some really fascinating data insights. Anyway, that's enough about EPOS. I could go on forever about the platform, but we're here to listen to Dr. Zwaan speak. So let me transition now to the introduction of the topic for our virtual coffee break. And thank you all for listening to a little bit of information about EPOS. So today in our virtual coffee break, we'll be looking at the Main Ethiopian Rift, which is part of the East African Rift system. And I have here on the map a representation of the East African Rift system. This map is not 100% accurate, so please don't plan any vacations to East Africa based off of this map. It's just to give you an idea of the geographical area we're speaking about. The East African Rift system is one of the largest geological features on Earth, and it stretches for more than 3,000 kilometers, running from the Afar region in northern Ethiopia all the way south through Kenya, Tanzania, and into Mozambique. And it's one of the very few places in the world where we can directly see a continent being pulled apart by plate tectonics. And you can see that sort of represented by the arrows there. And the main Ethiopian rift is in the northern segment of this system. And I have it illustrated here in this red box. And it's where Africa meets the Red Sea in the Gulf of Aden, and it goes all the way down to the Turkana region in Kenya. And the main Ethiopian rift is where the Nubian plate to the west, illustrated here, and the Somali plate to the east are slowly moving apart at a rate of just a few millimeters per year. So it's a very interesting confluence of activity, which I'm going to be more excited to hear about later during the talk. And over millions of years, this process could eventually open a new ocean basin right through East Africa. So now that we've set the stage about the East African Rift and the main Ethiopian Rift, here's where the puzzle comes in. Cutting across this rift is a huge feature called the Yerer Tullu Wellel Lineament. And I'm sure I destroyed that beautiful name. And you see it illustrated here with YTVL. And this lineament is a fracture that runs for about 700 kilometers westward across the Ethiopian plateau. And it's at a very different angle from the rift. By all accounts, a feature like this should not still be active under the current plate motions, and yet the measurements show that it is still deforming today. And this contradiction has left geologists with big questions. Did the rift and the lineament form at the same time or at different times? Did the direction of plate motion shift at some point in the past? Or is there another process at work that explains why this wrong way fracture is still alive? The research we're discussing today dives into that mystery. It looks at how strain, and strain is the stretching and pulling apart of Earth's crust. It looks at how strain can shift locally in surprising ways, and how that might explain the activity along this unusual lineament. And beyond Ethiopia, it offers insights into how rifts form and evolve around the world. So, having set the stage, I'm going to hand it over to Frank for a quick introduction, and then he can hand it back to me, and we will get into the coffee break. So, Frank, please introduce yourself.
Yeah, so thank you very much for having me here, for inviting me to this coffee break. So I'm Frank Zwaan. I'm working at the University of Lausanne. I'm a geologist. I'm specialized in plate tectonic processes. So think about the opening of East Africa or building mountain ranges like the Alps or the Himalaya. What I'm doing is partially field work, but also a big portion of my work is simulations or modeling in the laboratory, but also with computers of these kinds of processes. And that's exactly what we are going to talk about today. So I'm looking forward to work on that. One comment, perhaps. This work was done in Potsdam, at KFZ Potsdam. It's a big research center in Germany. And I'm currently in Lausanne, but I have to shout out to the people in Potsdam with whom I collaborated in the past. So looking forward to talk about this. Thank you.
Great, thanks, Frank. So let's kick off with our first question. So when you were approaching this area, this topic, what made you decide to research it?
So I have a bit of a history during my research, looking into plate motions and breakup of continents, so like in East Africa. And I started a project in the past where I was focusing on the Afar region, which is in Ethiopia, but a little bit more to the north, where the Red Sea, the Gulf of Aden, and the main Ethiopian Rift come together as a triple junction. And I did there field work in the area and also simulations of that area. And during this work, I got in touch with a local geologist, Amea Moulounet, and we started talking about, about about research questions in the area. And he mentioned at some point this one lineament which is active, which is east-west oriented east-west. It should not be active during more or less east-west extension. in the area. So we started talking, and he actually also came over to Potsdam, where I was working. He had a project there, and so we decided to do simulations. And the good thing also about Potsdam is that they have a beautiful laboratory over there where you can do this kind of thing. So everything kind of came together to do this project, and we got some really interesting results, I think.
And so, yeah, because it was laboratory based, you probably, I don't know, did you feel very prepared for this, or did you feel like you had still a lot to understand about it in the way, or did you feel more in control? What was your feeling because it was laboratory based, maybe versus field based?
Yes. So I've done a lot of these laboratory models, and it's a little bit in my blood, if you want. I mean, I've done a lot of these kind of things, so I could basically reuse the experience and the techniques that I've used in the past, reuse them in Potsdam by rebuilding a little bit the machine. These are pretty simple models, if you want. Um, and we also have some pictures of those, so you can maybe share that as well.
Yeah.
But I was pretty confident I could do this, and it's always, it's a bit of a creative challenge to actually do this kind of thing. So this is a picture in the laboratory with colleagues. You can see Amea in the back. I'm pointing at the laboratory or at the model, and these models, they consist of layers of sand that or simple materials that represent the Earth's layers. So we have sand and silicon. Sand creates kind of fractures. I think the next picture shows that a bit better, perhaps. So you can have these beautiful structures that really look like structures in nature. You can reproduce them in the laboratory by having a layer of sand that's being deformed. Um, and so we have here a layer cake of sand on top and silicon at the bottom. Silicon behaves a little bit differently. It kind of flows. That's to represent the deeper layers. And at the bottom, we have a plate that's linked to a motor, which is then pulling apart the sand. So you get this beautiful rift structure that represents what we can see in East Africa. So I've done this kind of stuff in the past. And so I was able to easily start this kind of modeling here. And this is one nice example. In the next picture, you can see how we can monitor these kind of models. You can have cameras, lighting, laser scanners to check what's happening on the surface. And the beautiful thing about these models is that you can trace the evolution because you have time-lapse data. And on the next slide, I think there is a little video that shows you the evolution of a model where the time-lapse shows where deformation is localizing. So the red and the black, these are faults, fractures in the earth or in the model, let's say. And you can see how the model is opening up. And you can see that to the left, that one yellowish reddish line, that's one of the lineaments. That's a lineament that's active. And this is kind of how we show that this is actually possible in nature to get this kind of activity by using the models.
Yeah, it's really, I think doing that time tracking is really fascinating. Did you, and I suppose because the laboratory is a very controlled environment, maybe this is a, I don't know if it's like the best question, but did your idea of a target change, or were you pretty certain with the outcomes? Because again, you were in such a controlled environment in a way, or did the outcomes surprise you, or were they accurate to what you predicted?
Yeah, so indeed, yeah, we were working in a laboratory, and what you do in a laboratory, these are simplifications of nature, but what you can test here are different parameters. For instance, the velocity of your motions, or the thickness of your layers, or the orientation of the rifts, for instance. That's very important. So we were thinking about, yeah, we want to reproduce nature in a very simple way, and we did one early model to kind of test the concept, if that worked. And we got indeed this activation of the lineament. So that seems to have worked pretty well. And then we had a couple of questions about different orientations or the
Hmm.
way that we implement this lineament. So we could test a little bit. The important thing is that you have to reproduce your model in order to make sure that your result is not just a fluke. So, you can have something that seems to work, but maybe you made a mistake somewhere. So you need to be very sure that your models are solid. And in this case, um, that worked. So we at the start we had a good result that was what we were hoping for, but we were not 100% sure. And when we were sure that we had it, we continued doing all the models in the parameter space, and then we had a good idea about how this mechanism or how this tectonic system here works.
So what were some of your takeaways after doing this? Like what sort of insights did you get into this lineament? What sort of insights did you get into this activity? And I suppose for the citizen scientist, like what's sort of the practical application for this?
Um,
Yeah.
Mhm. Yeah, so maybe one thing that's important to mention is that the activity of this lineament, which is east-west, is made possible by the orientation of the main rift. So there is
Mm,
the rift itself, it's oblique, so it's somewhat southwest northeast. That allows a deflection of motion that then reactivates itself the lineament. So that's the obliquity compared to the plate motion is very important. If the main rift would be north-south, we tested this, it wouldn't work. So that's maybe the key thing. We can have a deflection of motion, of plate motion, due to orientation. But beyond that, we can show that certain structures can be active where we were not expecting them to be active. And activity, if you talk about tectonics, that means earthquakes, seismicity. And so this structure here could be dangerous because earthquakes can strike whenever, and we can have fatalities or damage there. And this is another thing that can happen around the globe. If we do have certain structures that we think, okay, they might not be active, but in the end, due to this kind of motion or this kind of deflection of plate motion, they might actually be active. Then we have to consider that for danger to humans and
mm.
other things. It's important.
Sure. And I was going to promise I'm going to ask my multidisciplinarity question. So, Frank, if you could go back in time and you had all of the resources in the world and all the laboratory access and data access and everything, um, and you could carry out the research in like a fully inter and multidisciplinary manner, what other disciplines would you have liked to include it, or would you like to include in the future in regards to this? Like, and what else do you think you could learn by including those other disciplines?
Yeah, there would be a couple of things to consider. For instance, it would be very good to have earthquake data. So we have surveys that can trace earthquakes, and if we would have a really good survey in the area, you can see how active these lineaments are. There is actually a second lineament to the south, and I'm not sure if it's active or not. We don't have really data. So by having that data, you can better calibrate the modeling and your understanding. The earthquake data also allows you to understand what kind of motion you have, whether it's extension or compression or what we call strike slip. So
Hmm.
this is very important to understand the earthquake risk, for instance. So that kind of data would be very important. Also, GPS data, so that you can see what kind of motion is happening, so where the plates are moving and what kind of direction. That would be something. And another thing would be, in general, field data. So you could go in the field, you can measure structures, you can see what it looks like. Also, computer models would be very interesting too, because these models that we have
Hmm.
here, they are pretty simple. But with new computer models or numerical models, you can add a couple of components. Because one important thing that we didn't talk about is volcanism in the area. There's a couple of volcanoes along that lineament, and that might also be a component of deformation that we should consider. So there are a number of things that could be added. I'm pretty sure that the result itself here, it's really good. It's solid, but we can go beyond that, yes. And also in different areas, perhaps. So not only in this part of East Africa, but maybe the whole of East Africa. Or we can also better interpret perhaps the evolution of, for instance, the Atlantic, because there
Mm.
was a rift like East Africa in the past, but then we can better understand what was moving at what time. And this is also important for resources, for instance. So it's not only just earthquakes, but also resources in the end.
Frank, that was wonderful. Thank you so much. Do we have any question? I have a question, but do we have any questions from the audience, or any insights or something to share about the coffee break? Let me check the chat really quickly. And in the meantime, um, that scale that the model you built with your team in Potsdam, what was the scale of it more or less, Frank? I'm curious about that. Like when you were moving it, what did one, yeah, what were the scale in years and distance and things?
Yeah, so the model itself, again, is a simplification of nature, but the layers that we had is, I think, 3 centimeter thick in total, or 4 centimeter, which then represents the Earth's crust, something like 30, 40 kilometers. So 1 centimeter is about 10 kilometers. Um, and and the model itself was something like 50 by 50 centimeters. So it's not too large. And in this very small scale, you can model an area that's something like 500 kilometers square, or 500 by 500 kilometers. So it's a very useful way of it's a very practical way to understand large scale systems over time, especially since if we're talking about scales, there's also the geological time scale. So millions of
Right.
years, we are not able to understand or to follow this in our lifetimes. We will never see East Africa break apart in our lifetimes, but in the model, you can actually try to do that. So that's kind of the time scale. But if we're talking about the model itself, it ran something for a couple of hours, and that represents a history of about 20 million years. So 1 hour is about 10 million years of geological evolution. So that's kind of the time scale we're talking about.
Cool. Thank you. Yeah, that was my big curiosity. Any other questions from the audience? And it looks like we don't have any. So everyone can finish their coffee. Thank you for attending. It's almost lunchtime, where we are in Central European summertime. So thank you all for joining, and we'll see you at our next series. Follow us on LinkedIn to learn more. And Frank, thank you so much for taking the time to do this. It was really interesting and a lot of fun to prepare. And have a good day, everyone.
Thank you. It was a pleasure. See you next time. Bye bye.
Cheers. Bye.